Hello and welcome to this episode of the Industrial Engineering Notebook. The purpose of this video is to learn how to analyze the forces on 2D objects. I recommend you start by watching the point statics video, because this video is just going to be an extension of that. Okay, so forces and stuff. Force is really just mass times acceleration. Or more colloquially, we're using fancy words here, more colloquially, it's just pushing an object. And the unit of measure we use in the metric system is usually newtons. But in statics, we're not just worried about pushing an object. Once we get to the 2D case, we need to start worrying about rotation. That wasn't a concern when we were dealing with single points. I mean, what does it really mean for a single point to rotate? But when you're dealing with 2D objects, that stuff can rotate. And we call this rotation moment about a point. More often it's just called moment. It's sometimes called torque as well. And moment just equals force times perpendicular distance. And we'll talk about what perpendicular distance means in a little bit. But the colloquial way of saying moment is just rotating about a point. And the units of measure on this are usually Newton meters. So just imagine we're looking at the top of a table, we're looking down on this table, and there is a propeller. It's a really heavy propeller, and it's kind of massive, and it's sitting on this table like this. And I just put a pin in this propeller right there at the center, this heavy propeller at point A. That's where the pin is. And we know intuitively that if I put a force here, if I put enough force, maybe the propeller will move, but it definitely won't rotate. And it'll only move if I shear that pin, if I break that pin. That pin is going to resist any force that I put on it there. And same thing if I put a force here, or there, or there. So when will it rotate? And the answer is it's going to rotate if we add some perpendicular distance. So we have our force F here, and it has this distance that we'll call the letter D from a point. In this case, it's the pin on the propeller. So the moment or torque being applied to this propeller would be, we'll call that moment M. It would just be F times D. And if you decrease distance and put the force somewhere over here, well, the amount of torque that it's going to take to turn this heavy propeller that I've randomly pinned to this table, the amount of torque that it's going to take to start moving this thing has not changed. M has stayed the same. But our distance has decreased, which means our force to keep the same M needs to increase. So we'll actually need to apply more force to get this propeller moving if we push it at this point. And if we put the force over here, well, the distance is a lot bigger now. So we can put a lot less force to get that same amount of torque or moment. And maybe you don't have a propeller pinned to your table, but I'll bet in your house somewhere you have a door. And you can test this for yourself. The amount of moment it takes to rotate your door about the hinges is constant. It just depends on the door you have, the weight of the door, and the friction in the hinge. So that's not changing. But you can change where you apply the force to open your door. Try opening the door really close to the hinge. You'll notice you have to put a ton of force to open the door. Whereas if you apply that force by the knob all the way on the other end, it's just a little itty bit of force that you'll have to apply. But to turn the same door, it was a whole bunch of force really close to the hinge. So that's why moment is important. Moment is also important because in statics problems, we need one equation for every unknown that we have. For every force that we don't know, we need one equation so we can solve for all the unknown forces. And we already know two equations, so we can have two unknowns. Some of the forces in the x direction equals 0, and some of the forces in the y direction equals 0. So those are our two equations, which means in a statics problem, we can have two unknowns, up to two unknowns. But I'm going to use an example here with this horseshoe-looking thing, and say that someone is applying a 500 Newton force at a 40-degree angle, right there on this little horseshoe-looking thing. Let's say there's a pin there at point A, and a force here that we'll call F1, and a force here that we'll call F2. These are technically called reaction forces. And let's say we have an unknown force here called F3. We'll say this distance is 1/2 meter, We got 0.2 meters here, 0.2 meters here, and 0.3 meters here. And the best part is everything is perfectly drawn. So how are we going to solve for F1, F2, and F3 with just these two equations? Now is where we see the usefulness of moment, or another usefulness of moment. So we can take the sum of the moments about A, and that also is going to equal 0. Because not only is this horseshoe not moving in the x direction, and it's not moving in the y direction, it's also not rotating about point A. And we didn't have to pick point A here. We could have picked like a point here, or a point not even on the horseshoe, maybe somewhere out here. But point A is going to be the most convenient because we already have two forces that run through point A. There's no perpendicular distance for these two forces, which means there's no moment coming from these two forces, which means this is going to be much simpler to solve. So that's why we picked the moment about point A. Math time, I'll make this quick and painless. Sum of the forces in the x direction is going to equal 0, and we're going to call to the right as positive. So we're going to have the x component of the 500 Newton force here, which will be 500 times cosine of 40 degrees, and then minus F3 and minus F2. Sum of the forces in the y direction, where up is positive. We're going to have the y component of this 500 Newton force, which would be 500 newtons times sine of 40 degrees. And that will be negative because that component is facing down. And then plus F1. Sum of the moments about A, and we're going to call counterclockwise as positive. Moments can be positive or negative, and you just have to pick sign convention. So counterclockwise, we're going to call that positive. Sum of the moments is going to be equal to 0. F1 isn't going to have any moment about A. F2 isn't going to have any moment about A. F3 is going to have some moment because there's this perpendicular distance of 0.3 meters. And to determine if this is positive or negative, we just got to follow the force here. So F3, and it's going and it's going to kind of loop around A. And what direction is this? This is counterclockwise, which means this is F3 is giving a positive moment. So 0.3 times F3. And then both the x and y component of this 500 Newton force are going to provide a moment. So we'll start with just the x component. So remember, this was 500 cosine 40 degrees. So we follow this x direction and then loop around A. You see that we're going in a clockwise direction, so this is going to be a negative moment. And the perpendicular distance would be 0.5 meters. So negative 500 times cosine of 40 degrees times half a meter. And then the y component is also going to have a moment. Y component was 500 sine of 40 degrees, and that was pushing down. We go down, 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 and we loop around A. And we see what direction we're going. We're going counterclockwise, so that's going to provide a positive moment. Perpendicular distance here would be 0.2 meters. Plus 500 sine 40 times 0.2. This equation here is pretty easy. You just solve for F1. You'd find that it equals 321.39 newtons. In this equation, we can just solve for F3. Find that it equals 424.10 newtons. And then plug F3 up in here, and then we can solve for F2, which is 41.08 newtons. And this is why this is so important. Because all we knew at the beginning, if you remember, was that we had a 500 Newton force up here kind of coming in at an angle. But we didn't know what the forces were on this pin, and we didn't know what the force was over here. Using the magic of these laws, we were able to determine what kind of forces this pin was experiencing. If you're trying to design a widget and you know a pin's got to go there and you're not sure which pin to pick or which pin to buy or whatever, just from knowing that there's a 500 Newton force at an angle of 40 degrees up here, you can determine what forces are going to be at this pin all the way over here. And you can go on to select what material you want, diameter of the pin, and all that other stuff. If you like this video, please hit the like button. If you want to see more of these videos, the way you let me know that is by subscribing. And if you have questions, please put them in the comments.